Welcome to CS642 Computer Security. Today we'll be talking about the domain name system, or DNS, and security vulnerabilities. So let's start off with the motivation for DNS. If you think about how you actually send packets, as we talked about using IP, we need to send it to an IP address such as this IP version 4 address 128.105.5.31. The problem is we don't want to have to remember these IP addresses, so instead we would like to use names. These names are called DNS names. And the way this used to be handled was that there was a single table called the host.txt file that had the name of every single machine on the whole internet. When the internet was small, 1,000 machines, this wasn't too big. You can still have your own hosts file on every computer to list very specific, to list your own mappings of names to addresses if you would like. So in this case, we can see that the names spam and spam-test are mapped to the address 128.105.6.42. And that some other names, GE-1-2-Cisco1, is mapped to the IP address 128.105.1.2. So, needless to say, having a single text file wasn't very scalable, and so a system was put into place in the 80s called the domain name system that created a hierarchical domain namespace. There's an unnamed root domain, you can sort of call this dot. The namespace is divided into zones, and the idea is that these zones are controlled by different organizations. So there's some organization that controls the root, that will then will sort of delegate portions of the total namespace of all names to other zones that manage, for example, each top level domain. So this shows a zone at the top that has underneath it 5 different zones. Those zones can manage just a single level, or they can manage a whole tree of levels, some kind of subtree. And then you can have zones underneath a zone, you can have another zone. This is called zone delegation. So for example, WISC.edu can delegate the zone cs.wisc.edu to the computer science department so that we can manage all of our own names within cs.wisc.edu. cs.wisc.edu could delegate security.cs.wisc.edu to me, and that would allow me to create hosts under the security.cs.wisc.edu domain. So now that we have zones, we have to think about how do we resolve names. So the basic idea is that we are configured with some initial set of name servers, and typically there's some resolver that actually does the resolver here is called a recursor that will actually look up a domain. So you send a request to some DNS resolver recursor. It's configured with the names of the root name servers. There's typically 13 of these, and they hold mappings for all of the different top-level domains. So these root name servers we can go to first. So if we wanted to look up wikipedia.org, we'd go to the root name server and say, hey, we want to look up www.wikipedia.org. It would respond in saying, well, I can't handle that, but I know that .org is a zone underneath me, so try the IP at DNS server at IP address 204.74.112.1 and ask it about wikipedia.org. The thing to note is the root name server doesn't know how the zones are configured. It just knows about the next level below it. So the DNS recursor then goes to the .org name server and says, can you help me with www.wikipedia.org? And it will say, I can't help you, but try going to address 207.142.131.234 and ask that domain name server. Finally, the DNS recursor will go to the wikipedia.org name server and say, can you tell me about www.wikipedia.org? And it will say, oh yeah, this is that at address xxx.xx.xx.xx. So the idea is this is a recursive, it's sort of an iterative lookup or recursive lookup where we start at the root and work our way down, and we get referrals at each stage to sort of tell us who we should consult next. So DNS supports multiple types of information. The most common kinds of information are A records. These are IPv4 addresses, or AAAA records. These are IPv6 address records. We also have NS records. They can say, for a domain name, what is the name server that handles that domain name? So those are the records that we were returning in the previous case when we were getting back name server information of which name servers handled wikipedia.org. There's also TXT records that have human readable text. This can also be used to add sort of extra information for some encryption mechanisms. And finally, there are MX records, or mail exchange records. This tells you if you want to send mail to somebody at a domain, how to find what mailbox to send it to. And this is sort of unique in a way that it's specific to a protocol. The other ones are much more generic about host names. So there's different kinds of domain name servers. One is an authoritative name server. Authoritative name server only returns names that it's actually been configured by some original source. This means that some administrative server told the name server, here is a mapping from an IP address to a host name, and you are authorized to give the correct answer. So when an authoritative name server returns a response, it sets the AA bit, authoritative answer bit, in the response. And anybody who gets this answer can say, oh, I got the real answer because I got it from the source of the name servers that actually know the truth. In contrast, there are caching name servers that may do lookups on your behalf. So for example, you as the client may not actually do that iterative query I just showed you. You may talk to some other DNS server, for example, run at your ISP or running in your router, your home Wi-Fi router, that does the recursive lookup for you. And so it is sort of a caching name server that does lookups and return cache results. So this is nice because it speeds up queries. If you ask for the same thing twice, it can return the answer very quickly. It can also cache both positive and negative responses because it can, when you look up something and there is no name there, if you mistype a name and it fails, it can cache that so it doesn't have to go look out on the internet again. The way consistency is handled is that cache names have timeouts on them, and so the results will periodically time out and be refreshed. If the refresh rate is very low, like 1 second, then they'll only be used for a short period. This is good if you want to sort of load balance a single domain name across multiple hosts. The name can also be very set to a very large TTL if it really never changes. So for example, a host name of your desktop machine may have a very long TTL because its IP address never changes. So let's look next at the format of a DNS packet on the wire and walk through the protocol. So this is the format of a DNS packet. This is taken from a paper listed on the webpage Friedel on how DNS poisoning works. So DNS is an IP protocol. So we at the top have the standard IP header, which has the information, the source and destination IP address. It uses the UDP protocol, so it has a UDP header, which has a source port, destination port. This indicates where to send messages to and where to receive responses. Has a length field to say how long it is, and a checksum to sort of make sure it isn't corrupted. And then finally, there's the DNS protocol level itself. This has a query ID, which makes this unique, and a bunch of other fields where you can supply questions and get answers, and then a data field. So let's now sort of look at how this protocol actually works. So this is a query from a DNS resolver to a name service. We've got the source and destination IP addresses in there. So this is a request coming from a recursive DNS resolver at spcglobal.net. That's the source. It is talking to a top-level domain server, c.gtldserver.net. So this is one of the top-level domains. We've got a source port 5798. This is sort of more or less a random port. The destination port is 53. This is sort of the standard port for all DNS servers. So the destination port for a request will almost always be 53. We then have a query ID. This is like the IP ID or the TCP sequence number. This is just a random ID. And the ID here lets us match up a request with a response because a DNS resolver may have thousands of outstanding requests being processed simultaneously. We then have some bits. So we have a recursion desired, which says that when we ask the next level, if it doesn't have the answer, do we want it to go try to find the answer itself or to just tell us where we should go and we'll do the lookup. So if it's 1, then we want recursion. Here we're 0. And then we have some bits saying that this is a standard query. And then in the question field, we have one question. And the question is, what is the address record for www.unixwiz.net? So this is sent to a top-level domain server. And so it doesn't know the answer. It's going to refer us. So we swap the source and the destination IP addresses. We swap the source and destination port numbers. We keep the same query ID so we know where it comes from. And we're sending a response. So here QR equals 1 that says it's a response, but it's not authoritative because we're not actually returning an address that we have the authoritative answer for. And we're saying recursion is unavailable. Even if you wanted it, the top level domain servers don't do recursion. So there was one question, but we have 0 answers that we're replying with. So instead, what the top level do is it provides referrals. So it provides 2 authorities, and it says that we have 2 additional records here. The authorities are DNS names of name servers that know about the unixwiz.net domain name. So these are the 2 authorities. The additional records are the A records or the address records for these 2 servers. And we do this because this avoids having the client have to go then do a separate name server lookup for these 2 name servers, linux.unixwiz.net and cs.unixwiz.net. Because the IP addresses are given. So note that the name servers have a 2-day lifetime because the name servers don't change very often. The addresses have a 1 hour lifetime because they might change. So one thing to note is that if a DNS resolver gets a query ID that doesn't correspond to any query IDs that it sent out, it will just drop the request. So having received this, it will now send another request. It'll go to the next server. So here we're sending a request to linux.unixwiz.net. We have a new query ID. This is incremented by 1. We're requesting recursion. It's a standard query. We have one question, and the question is, what is the address record for unixwiz.net? Here we get a response back, and what we see is that we have answer count is 1, which means that we actually are going to get an answer back. We have AA equals 1. This is an authoritative answer, so it's from a name server that knows sort of the ground truth here, and it provides in this A record in the answer field, it provides the IP address for www.unixwiz.net, which is 8.7.25.94. It also provides usefully the authority information that says what are the name servers for this domain and their IP addresses in case the client doesn't have these, so it can sort of see these things. Now, one question is, how do we know if we get a response that we should actually believe what it says? So, for example, you know, a rogue DNS server could respond with answers about any domain. So, for example, the DNS server for the CS department could return www.google.com is some address in the computer science department. So this is handled by bailiwick checking. And what it does is it checks to make sure that the name that is being responded to, www.unixwiz.net, has as a suffix the authority that are listed below, unixwiz.net. So this makes sure that, so this means that the name server responding has the authority to actually answer for this. If the authority was, if it sent back, you know, b.com instead of unixwiz.net or google.com instead of unixwiz.net, the authority wouldn't match, and the client would say, I don't trust this response, I'm going to drop it because you're not authorized to answer for this request. So here we go again. We have a protocol that is just using IP packets, UDP packet sending back and forth. We have no encryption. We have no message authentication codes. We're sending names back and forth in the clear. Let's sort of think about what security we have. Well, we have query IDs that link responses to queries. So we know if we get a response what query it came from. You know, there's a question, do these need to be random or not random? And you can sort of guess probably they need to be random. We have bailiwick checking, which sort of says, is the name we looked up sort of in the authority or the bailiwick of the server? Now note this is a sanity check because a faulty DNS server could include a different set of authorities with different names that would make the bailiwick check pass. But note there's no authentication. We don't know who this DNS server is. We don't know that it's a real DNS server. It's not just some random packet. And furthermore, there's lots of things that trust the host-named IP mapping. So when you are a browser connecting to a server, we use the host IP mapping for the same origin policy because we assume that the DNS lookup will go to the right servers. So if we have some way of poisoning DNS, we can get your browser to go to a machine under an attacker's control, thinking that it's the same origin, but it's actually some other thing. The URL in the address bar also shows a domain name. It doesn't show the IP address, and so you have to trust that DNS is returning the correct IP address. So what are the clear problems? Well, one problem is a corrupted name server that could return all kinds of bogus information. Here, you know, the solution is configure clients not to talk to corrupted name servers. Don't let somebody propose a bad name server to you. Don't take NS records for domains that you care about that point them at corrupt name servers. Another thing is an attacker can intercept and manipulate requests and responses. So an active network attacker could potentially see a DNS response and just modify the IP address in it so that a client would go to the wrong place. And if you can have active network attacks, there's really zero protection against this. So are there other obvious issues of things that might happen? So think about this a little bit. Pause here before you go on. So one thing you can do is DNS is a network service. Everybody uses it. As I said, there's only 13 root servers, and so that's not that many servers for the whole internet. So if you can do a big denial of service attack and you take down the root servers, then nobody can use the internet because nobody can look anything up. So in 2007, 6 of the 13 root servers were attacked via distributed denial of service attack that really slowed the whole internet down. So the Department of Defense had an interesting response. In the event of a massive cyber attack against the country that was perceived as originating from a foreign source, the United States would continue launching a cyber attack, counterattack, or bombing the source of the cyber attack. So this is sort of saying that an attack against the DNS infrastructure is a military attack, and then it might be responded not with an electronic or a network response, but with a physical security response. So denial of service attacks are interesting, but they're not necessarily that clever. They're valid, but they're not necessarily that interesting or clever. So let's think about what more clever things could happen. So the standard attack against DNS is what's called DNS cache poisoning. And the idea here is there some way that we can stick a bad IP address to domain name mapping into the cache of a DNS server? And if we can do that, any clients using that victim DNS server will then go to the wrong address. So the question is, how can we get a victim DNS, a bad thing in here? Basically, what we need to do is to send a DNS response packet that the victim DNS server will accept, and will accept the addresses and IP addresses and domain names from that response. So here's a description of how it works. We start at the bottom with this lookup. We want the IP address of the bad guy client, but the goal here is we want to attack a victim name server. So our goal is we want to attack www.bankofsteve, and we want to stick in a fake address that goes to the fake bank of Steve into there, 10.9.9.99. So the bad guy client here will go to the victim name server, and it will say what is the IP address for bankofsteve.com. The victim name server will then go query the top level root servers for .com, or it'll go query for bankofsteve.com. With query ID 1000. The top level servers will respond with query ID response 1000 with a referral to the Bank of Steve name server, ns1.bankofsteve.com. So at this point, the victim name server will send out message 4. It'll send a query ID to the real Bank of Steve name server, expecting to get back response message number 5, which says the real address is 10.1.1.1. However, what the bad guy can do is to start sending DNS response queries to the victim name server as soon as it sends the request. So this is 2A, and it will just send out, it will send addresses with a source port, Bank of Steve's name server. It knows this because it can do a lookup to find out where this is itself. It doesn't know the query ID, but it can sort of guess the query ID potentially. Or it can just flood lots of requests with lots of different query IDs, and the victim name server, if it sees a matching query ID, will accept the response, and then when it gets the real packet from the Bank of Steve network, it will drop it because it's a duplicate. It'll think that the Bank of Steve response is a bogus response that it got second. So this allows us, if we're fast enough and we guess the query ID correctly, to actually inject a packet. So here, if the victim name server, for example, has predictable query IDs, then we can sort of send a message to it to sort of see what the query ID is. So for example, we could send a request for the victim name server that actually went to a bad guy domain to sort of figure out what query IDs it's using, and then guess query IDs that are a little bit bigger than that. So this only attacks a single host name. What if we want to sort of poison a whole domain? So here what we want to do is we want to fake the response from the top level servers that give us the name server for the Bank of Steve domain. If we can fake that response, then the victim name server will actually go to our bad guy name server. So here we have the bad guy client ask for the IP address for some random host at www.1234567.8.bankofsteve.com. Now the host name is random here because we want to make sure that it's not cached in the victim name server already, because we want the victim name server to go look up records. So the victim name server will go to the root with this is message 2B and ask for bankofsteve.com. It gets the referral response to ns1.bankofsteve.com. It sends a request to bankofsteve.com for. It gets a response from bankofsteve.com. For this random address, it'll get an error response because it doesn't exist, but it will also get back the IP address 10.1.1.1 for name server bank.steve.com. So here what we do, as soon as the bad guy client sends the request for Bank of Steve, www.1234567.8.bankofsteve.com, it's going to send message 2A, which is a query response listing its IP address as the location, as the address of the bankofsteve.com name server. Now note that it can use the real name server for bankofsteve.com because it's providing the IP address. And so this makes it harder to see. So the victim name server, when it sees message 2A, will actually use message 2A instead of bank of 5, instead of message 5, the real response, because we guessed the right query ID. So then when it does the recursive lookup for bankofsteve.com, it'll go to the bad guy network, and we can return whatever we want here, and one of these with the correct query ID to actually respond. So the key thing here is that if we can send enough packets and guess the query ID, we can guess the port number, we know the port number the victim name server is using, we can inject responses that were never sent. That's why it's called poisoning. So let's think now about what the defenses are here. Well, we're sort of limited by the protocol. So the query ID is only 16 bits, which means that at 64 bits is a lot to guess, but your chance of getting one right if you try enough times is actually pretty high. So one thing we can do is we can repeat each query with a query ID. So we actually try queries twice with different query IDs that are each random. So this makes it a lot harder because you have to guess 2 correct numbers instead of another one. We can also randomize the UDP source port. Instead of just always using the same source port, as long as the DNS resolver runs, we can have a different source port for every single DNS request. This means that you have to guess the right DNS source port and query ID combination to get it right. Finally, we can use DNSSEC, which is a way to cryptographically sign DNS responses. So this says we put a digital signature on the DNS response that is signed by the authoritative name server. And we also have the name server record signed saying that this is the right name server. So we can sort of look at a certificate chain from the root on down saying that this is indeed the correct mapping. And then the client just has to verify the signatures are correct. So unfortunately in practice, this is really only used by top level domains. So you can see for Internet 2, it's only enabled on about 10% of machines. For ESNet, it's on 91% of machines. But it's not sort of completely universally used yet. So of these top level domains, it's used by about 75%. But that's just the top level domains and not lower level downs. So DNSSEC should work, but introducing these protocols in the internet takes very, very long time. So a final problem with DNS is where do the names come from? So sometimes they're in an email or they're generated by a program and then they're usually correct. But a lot of times people will type in the domain name and they might type it wrong. This is called typo squatting when you register a domain name that is a small, sort of a simple misspelling. So www.ca.wisc.edu instead of CS. So here we look for other keyboard letters on the keyboard that are nearby the right letter to find common typos. Or we might have www.goggle.com instead of google.com. The other thing we might do is we might have URLs that have lots of garbage in them. So when somebody looks at the domain name, they actually sort of see the end of the URL, which says google.com, but they might not see the badguy.com at the beginning of it. You can also have, www.google-wisc.com, which is, you might think is a google.com name, but might not be. So the idea is these are really just trick users into thinking a malicious domain is a real one, and that way it's like a phishing attack. If you go to goggle.com, this is the kind of thing you might get instead of the real result. So that concludes our discussion of DNS security, and we will pick up with other network security protocols next time. Top level domains are TLDs. These are the ones we're used to, .org, .net, .edu, .com, .tv, .ca for Canada and for other countries. Underneath that, we have second level domains, wisconsin.edu, ucsd.edu, davis.edu, berkeley.edu. And below that, we have third level and fourth level domains, cs.wisc.edu, www.cs.wisc.edu. The total domain name has a maximum length that can be, I believe, 256 characters. Each element in this, such as www or wisc or edu, can be up to 63 characters. And so the thing to note is the whole domain is made starting at the root, walking to the leaf, putting a dot between each one. And so the shorter the name, the closer you are to the root. The longer the name, the further you are from the root. So the